Hello, my name is Mr. Pratt and this is Electricity Lesson 12. In this lesson we're going to be looking at combinations of resistors, which is part of the required practical. For the lesson you're going to need a pen, paper or an exercise book to record some notes in, and unless you're watching this video on your mobile phone, get it on silent, turn it over, get it out of the way and avoid as many distractions as you can. Straight on to the starter then, I'm going to give you 2 minutes. I want you to explain how connecting the 1.5 ohm bulbs together in the two different ways on those two different diagrams affects the current that flows. Okay, 1 minute left. If you finish, you might be able to work out the current that's flowing in the two branches on the bottom circuit. Right then, so if we connect the two bulbs in series, the total resistance will be higher because the resistance is the same as the two of them added together. But on the bottom diagram we've connected them in parallel. So the total resistance in a parallel circuit is less than the smallest resistance that we've got there. And because the resistance in the bottom circuit is less then, we get more current flowing. So in the bottom circuit we've got 4 amps coming out of and going into the cell, and then that'll divide up so we get 2 amps going through one bulb and 2 amps going through the other. So the bulbs would actually be brighter on the bottom circuit than they would be on the top circuit. Outcomes then, we're going to make sure we can describe how to carry out this required practical when we've got resistors in combinations, series combinations and parallel combinations. And then we're going to look at the data we've collected, suggest improvements and see if we can see anything wrong with it. So we're going to evaluate the data that we've got. So the required practical then, we've previously done something very similar where we've investigated how the length of a wire affects its resistance. Now what we're going to do now is the same, but not a wire that we change the length of, but put in different combinations of resistors in there instead. So the equipment they're going to need and the way that we carry out the practical is very similar. This is the equipment that you will have used before to measure the resistance of a wire. So you need a power pack or a battery. You connect the ammeter in series, so the current will come out of the power pack, go into the ammeter, come out of the ammeter, then go through your wire and back round to your battery again. you've got to connect the voltmeter in parallel. So if you look at the voltmeter in that diagram, it's just connected to either side of the wire. Crocodile clips to connect it onto the wire, leads, and then you've got your metal wire on a ruler, and you can move the crocodile clips up and down. On this diagram here, we've not got crocodile clips. We've got, it's called a jockey, but it's a bit like the end of a screwdriver and it's a little bit sharper. It allows you to get a more precise reading because it's a bit sharper and you can see exactly where you've got the length to. So the insert bit there, it's 57.2 centimetres is the length of wire that we're using. We're going to do the same thing then, so it's pretty much the same setup, but we're going to put in different resistor combinations. So the apparatus that we're going to need, very similar to before, power pack or battery, ammeter that we're going to put in series, voltmeter that we're going to put in parallel, crocodile clips and leads. And then we're going to have a selection of different resistors. We can find the resistance of one resistor. We can then connect them in series and we could find the total resistance of those. Then we could find the total resistance of 3 in series. You could do a lot more if you've got time. And then we can connect them in parallel, so we could have 2 in parallel like that, so we'd find the resistance of them pair. Or you could put 3 of them in parallel, find the resistance of those pair. There's all sorts of combinations that you can do, but those 4 different combinations, if you can measure those, that'll pretty much be good enough. Let's set up then and have a look how we're going to find the resistance of resistor combinations. We've got a straightforward resistor, it's marked 10 ohms. We'll measure it in a minute and we'll have a look how close to 10 ohms it actually is. So we can set up and find the resistance of this, but we can also then set up and find the total resistance if we connect them two like that. So that would be connecting a 10 ohm with a 10 ohm in series. And then we could put another one in and we could find out the effect of connecting 3 of them in series. But also we could connect 2 resistors in parallel like that and then find the total resistance of them. So we can do different combinations. You don't have to be 10 ohm resistors, you could do any that you like, but we'll measure a few and see how it comes out like and see how much time we've got. Got a power supply set on 2 volts. I've set it pretty low. I don't want it to get too hot and end up these being damaged by too much current. So we'll put 1 10 ohm to start with, out of the positive side of the power supply and into the ammeter. Then from the ammeter into one side of the resistor, and then from the other side of the resistor back into the power supply. So the ammeter's in series, the current goes through the ammeter, current's got to go through it so we can measure how much current is flowing, and then through the resistor back into the power supply. Then I need my voltmeter. The voltmeter needs to be in parallel, it needs to be across the thing that we're interested in. We're interested in that one resistor, so we connect the voltmeter across the resistor like that, and we can measure the total potential difference across it. Switch it on. Make sure that's pushed in. It's pushed in. And it's just settling down. It's fluctuating a bit. We've got a potential difference and we've got a current. So to stay still. That's staying fairly still. So the potential difference, V, is I'm going to go 1.25 and the current I 0.10. Switch it off to let it cool down.
Find the resistance then. The resistance is the potential difference divided by the current, which would be 1.25 divided by 0.10. But I've spotted a problem. Anyone else spotted a problem? Right, this is off. Potential difference is reading 0. We've got a problem here. This is reading minus 0.05 amps when it's switched off. Still reading it now. Now you'll come across this from time to time. It's unusual to come across it with a digital meter like this. You do come across it with balances, and there's a button on there that you can reset it. We call that sort of error a zero error, because an instrument is not reading 0 when it should be. That should be 0 and it's reading minus 0.05 amps. There's a couple of things that you can do. You could get another one or reset it. I haven't got another one and you can't reset it. So the only other thing that you can do is to take account of that with the readings. So for the current, we got 0.10, but it was already reading minus 0.05. So we need to take that into account. So it shouldn't have been 0.10. We need to add that on. It should have been 0.15 amps. So that's taken account of that zero error. So it should have been then 1.25 volts divided by 0.15 amps. Let's do that on a calculator and see what resistance it gives us. It should be about 10. 1.25 divided by 0.15, 8.3. It's a bit off, but we'll write that down. So 8.3. We've got two in series now, so I've got a 10 ohm and a 10 ohm connected in series. Let's switch it on, remembering to take account of that zero error. So that was the first resistor. Now we've got potential difference of 3.71 and we've got a current of 0.10, but remember it was reading minus 0.05 to start with, so we need to add that on, 0.15. So that's actually the same as before. The current's the same as before, but I've got an increased potential difference. I did turn it up just to get a slightly bigger value. So let's do 3.71 divided by 0.15 and see what total resistance I get with the two in series. 3.71 24.7 ohms. Now I'm not going to do any more, but I could put another one in series, or I could start connecting them in parallel. Now in a bit I'm going to change the equipment. I've got an easier way that you can do this, as long as you're aware of how you use the voltmeter and the ammeter when you're doing this practically. There is a bit of a cheap way of doing it, a bit quicker.
Let's have a look at the equipment that we needed then. So this is a very common circuit diagram that we'll need to draw to measure the resistance of something. So this is really worthwhile remembering. If you want to pause the video now and draw it when it's all on there, then do that, but it also appears on the summary slide at the end of the video. So we've got a battery. We connect the battery to an ammeter, and then in that gap we pop in our resistor combination. So there we've got two resistors in series. We've got to remember to put the voltmeter across it. The voltmeter needs to be in parallel, so we want to know what the potential difference is across both of them, so we put the voltmeter across both of them, because remember we're trying to find the resistance of the two of them together, the combination. A variable resistor in that circuit there can be useful because you can use it to reduce the amount of current, so you can stop it heating the resistors up, so you can keep your current low with that, both from a safety point of view and because if your resistors are getting hot, it's actually going to increase their resistance. As long as your voltmeter is across just the two resistors that we're interested in, when we do our calculation, it's not going to include the resistance of this variable resistor, so it won't affect the results you get, apart from keeping it cool and safe. In summary then, ammeter in series with the resistor combinations. The resistor combinations have then got the voltmeter across them, so the voltmeter's in parallel with them. And a variable resistor can help to reduce the current and stop the resistors overheating. Got a diagram there of the ammeter that you saw me use. Let's talk about zero error. So the ammeter wasn't reading 0 before it was connected, so if it's not reading 0 and it should be, we call it a zero error. There's two sorts of errors you can see from the keywords at the bottom. There's a random error and there's systematic error. Zero error is an example of systematic error. That's because it's part of the system, it's part of the way that you're doing the measuring, so it can be caused by faulty equipment, like we've got there, or it could be to do with that equipment is being used. And it'll cause an error in every reading. It's systematic, it happens all of the time. So it's not a one-off thing, it'll affect all the results. What we did then, because we couldn't reset, there's no reset button on that one, we had to make sure that because it was reading minus 0.05, we need to add 0.05 on to all the readings because it should have been bigger than the display was saying. Another example, potentially, of a zero error is using a ruler. I'll just give you 20 seconds. So if the student wasn't careful using that ruler, how could that cause a zero error? Let's say they were just measuring the distance that something was falling. That ruler, the very end of that ruler, is not where 0 is. So if you're not careful and you measure from the end of the ruler, so you push the end of the ruler into the position that you want to start measuring from, you're going to end up with a zero error, because if you were to measure 2 centimetres, it's not really 2 centimetres because you've included the bit at the bottom. So you'll end up with a reading that is lower than it should be by, looking at that, about 3 millimetres. So that's another example of a zero error. Let's get some values off here. So the voltmeter was giving us a potential difference of 3.71 volts. This is across the two resistors in series. The current, well, the ammeter gave us a reading of 0.10, but we had to add on 0.05 because of the zero error. So we had a current flowing through our two resistors of 0.15 amps. Resistance is potential difference divided by current. That comes from the equation V equals I times R. Pop the numbers in. So 3.71 volts divided by 0.15 amps gives us a value, the three significant figures, of 24.7 ohms. If we wanted to do that with 3 resistors in series, calculation's just the same, but we'd need to make sure that the voltmeter was across all 3 of the resistors in series, and we get a different value, and we get a resistance that should be higher than that, because putting resistors in series, the resistance of the circuit increases.
Right, let's look at alternative methods. So the alternative method is not to use power pack, ammeter and voltmeter at all, is to use one of these, which is a multimeter. Multimeter can be used for measuring potential difference, that's AC on that side, DC potential difference this side. It can be used for measuring current. This one won't do AC, it'll just do DC, and depending on where you put it, it will measure up to different amounts. If I slide that down to the bottom there, it will read up to 200 ohms. So now this is working as a resistance meter, an ohm meter, so it's measuring resistance directly. By using this, I don't have the problem of overheating by getting too high a current, and also it's a lot quicker and a lot tidier to use. As long as you understand the previous circuit and putting the voltmeter in parallel and the ammeter in series, you could probably get away with explaining this required practical by using a multimeter and measuring them directly. It's a little bit easier to explain. You don't need to record any values. I'll stick all the values on the video afterwards. So I'm going to start off just measuring the resistance of a resistor on its own. So I've got 10.2 ohms for that one, 10.2 ohms for that one, 10.1, 10.2 ohms for that one. So for the sake of simplicity, I'm going to say that the 10.2. So you'll notice straight away that even though they're marked with 10 ohms on, in actual fact, that's only an approximation. So it's 10.2. So be a little bit careful with that, because you might find that it confuses you when you don't get the values that you're expecting. So we're going to say that they're all 10.2. We'll start off then connecting two of them in series. So we'll do the series first. So series, they're just next to each other, and then I connect on there. So let's have a look what 2 in series looks like. 20, 19.9, let's do it again. 20 ohms. So that gives 20 ohms of 2 in series. Let's put an extra one in. So now we've got 3 10 ohm resistors in series. Again, connect across the ends. Just waiting for it to settle down. 34. Just going to double check, trusting that I've got a good connection in those two. So it's still 34. Ah no, I had a slight poor connection there. That's, I'm going to call it exactly 30.0. So 30.0 for the 3 of them. And that's measuring combinations of resistors in series. And on to putting resistors into parallel. This time I'm going to connect them like that. So that's 2 10 ohm resistors in parallel. And then I'm going to just connect that across there. 5.3 ohms. Let's put a third one in. Oh. 3.7 ohms.
Here's the results then that I've popped into this table. I've just done it with a diagram, so you can see on the second one down we've got 2 resistors in series, and that gives us 20 ohms, and each resistor, if you remember, was 10.2 ohms. Got some questions for you to do. I'll give you 2 minutes. So question 1, explain if the results are what you expected. Number 2, what else would you need to do to see if the results are precise? I'm just checking that you understand that word precise there. I will go through all of these when you're finished. Don't worry if you can't do the odd one of them. Number 3, what random errors could have affected the results? And 4, what was the resolution of the multimeter when we used it as an ohm meter? 20 seconds left. First one then, see how you get on. Explain the results of what you would have expected. Well, if it's 10.2 for one of them, I'd expect two of them in series, it'd be 10.2 plus 10.2, so that's 20.0. So they're pretty close. You'd expect 2 times 10.2 to be 20.4. So yeah, that's pretty close. And the third one, that's pretty close as well. So they're pretty close to what we would have expected. The results for the resistors in series, in parallel, are close, but they're slightly too high. So if we had two 10.2 ohm resistors and they were connected in parallel, we should get half. It should go down to half the value because there's 2 routes that the current can take. So that should give us 5.1. And then 3, we've got 3 routes, so it should be 10.2 divided by 3, so it should be nearer 3.3. So they're a little high. It's possible to explain results being a little high just from the leads. If one of the leads that I was using, its resistance was a little bit higher, that would give us a systematic error, so that would be adding to the resistance of all of them. Number 2 then, what would you need to do to see if the results are precise? Precision, you can only, see if someone has been precise taking the readings, if you can see lots of other versions of the same reading, so you can compare them. So what you would have to do is to take repeat readings. If you then take repeat readings, and those repeat readings are very close to each other, we can say, well, there's good precision there. I was very precise when I was taking those readings. So you've got to have repeat readings to look at precision. I'll give you an example of some precise readings. It could be 20.0 ohms, and then I do it again, and I get 19.9. I do it again, and I get 20.0. I do it again, I get 20.1, and again I do 20.0. So I can tell that those are precise because they're very close to each other, and the closer they are, the more precise they are. Number 3. What random errors could have affected the results? So not systematic errors, so we're not talking about the 0 error that we had on the ammeter this time. A systematic error is one that happens all the time, could be a piece of equipment, affects all the results. So that's not what we're talking about here. If you had a lead that was incorrectly plugged in, and that did happen, I didn't take the reading though, I realised it was a bit high and double checked them, but that would cause a random error. So it'd affect 1 or 2 results, and it would have made the result a little bit too high because of the extra resistance from the lead not being plugged in correctly. So that'd give you anomalous reading if that was the case. So taking repeat readings, so we talked about repeat readings on the last bit, you can check if something is precise. But taking repeat readings will help you to identify anomalous results. And then if you've got anomalous results, you can see them and then you can do something about it. So taking repeat readings can help you reduce random errors. Let me give you an example. We've got those 5 values that we've taken, 20.0, 20.2, 22.8, 20.2 and 20.0. They look pretty precise to me apart from one. So there's an anomalous result. So if I then say, right, it's obviously anomalous, I'm not going to use that one. And then what I can do with the other 4, I can find a mean by adding them up and dividing by 4. So I'd get a mean result, an average result of 20.1. And then I would use that one. So I've reduced that random error. Number 4, what was the resolution of the multimeter when we were using it as an ohm meter? You can see from the results in the table there. Resolution of the multimeter was 0.1 ohms. So 0.1 ohms, that's the smallest value that it can measure on that setting. So that's what its resolution would be. Going to give you 4 minutes with this exam question now. The 6 mark bit, you're describing how you'd determine the value of that resistor using the circuit, similar circuit to what we've used. So 6 marks, you can do it in bullet points, you don't have to do extended sentences. And number 2, explain why the student should open the switch after each reading. So 4 minutes. Just approaching halfway through your time. Just be trying to get as close to that 6 marks as you can. Can you think of anything else you could put down? Should be just finishing off. Right, I'd like you to self-mark now, and then you'll end up with a mark out of 8. I'm just going to pop the mark scheme up and then I'll talk you through it. They're just looking for any 6 points here. I just look at the circuit and I'd think, right, what do we need to do to get this working? Well, you need to put the switch on. So you get a mark for saying the switch is on. You get a mark for saying that you're going to read the voltmeter and the ammeter, or just for saying I'm going to read the meters. That's 1 mark. Jumping down the mark scheme a little bit, you get a mark for saying you calculate resistance by doing potential difference divided by current, so that's a mark there. For any more marks, you need to talk about getting more than 1 reading. So you could take repeat readings and do a mean, that'll get you a mark. Or you could draw a graph and you could plot a graph of V against I, so the potential difference against the current. You could even do the gradient of that if you put the potential difference on the y-axis and the current on the x-axis. So have a look what you've got, see how many marks you've picked up. I would have thought you should have picked up 4 on that, if not more. Part 2, there's an easy mark and a more difficult mark here. The easy mark is to let it cool down, or the resistor would get too hot if left on. So if you've said to let it cool down, that's 1 mark that you've got. But it's not just a health and safety concern, stopping it overheating. If that resistor does get hot, its resistance would go up. All metals, when they get hot, because the atoms are vibrating more, you're getting more energy lost in collisions. So heating it up will actually stop your fair test, if you like. So well done if you've got 4 or more out of 8. Going to leave you with a summary. I've given a definition, well, not so much a definition, a description of the words resolution, systematic error, random error, repeat readings. Make a note of those if you've not got them. And then on the left-hand side, we've got the diagram of the circuit that we used, and that's where we've got 2 resistors in series, but you just put your different combinations in that gap. I've explained that the resistor combinations need the voltmeter across them in parallel and the ammeter in series, and why the variable resistor is there, so you can reduce the current and stop the resistors overheating. Well done for working on that. I'll see you next time for the next lesson on electricity.